So our next speaker is Oren from University of Toronto, talking about influence at scale, distributed computation of complex contagion in networks.
Sorry, there's. Put something here that would prevent it from flipping. Is that okay? Okay. So this is joint work with Yaron Singer and Brendan Lucier. All right, so what am I going to talk about today? So I want to talk about influence cascades in social networks. So social networks, as we all know, are now pervasive, and moreover, they're massive today, right? And so I'm going to talk about today about influence cascades, where some contagion spreads in the network, like viruses, influence product adoption, memes, opinions, and so on. So what we'd be interested in doing is estimate the spread of such contagions. And so what are the known methods for doing this estimation? So just to give you two examples, one is doing sampling type of approaches where we sample polynomially many samples, and then we take the mean, and that would serve as an estimate of the spread. Other class of algorithms do linear algebraic things to estimate these spreads based on different types of models. And in this talk, we'd like to focus on whether or not these approaches scale to massive networks. All right. So what do I mean by that? So what is the general question? So the general question is what is the information cost of estimating these spread measures? So how much of the graph do we actually need to look at in order to compute these functions, the spread, and how much information do we need to store during this estimation? And moreover, we'd like to design algorithms that scale well by using distributed methods to doing this estimation on massive social networks that use frameworks like MapReduce and so on. So what is the related work? So what is the background? So this can be divided into three major topics groups. So the first group is the analysis of massive graphs. So this is a highly studied topic nowadays. HPC people do a lot of work on that. So there are basically two schools. One is single machine frameworks for doing that, like Cascade, LiGraph, Snap. The other school is distributed computing, like Hadoop, MapReduce, Spark with GraphX, and so on. Second group of work is algorithms for doing these, theoretically capturing the MapReduce and other parallel computation paradigms. So the relevant theoretical model that we'll be looking at is the Mrc model proposed by Karloff et al. So it basically captures MapReduce, and a lot of algorithms on graphs have been proposed using that adhere to this scheme, like that do connectivity, MSTs, matching, and so on. Third group of results pertains to influence diffusion. Models of influence diffusion have been proposed as early as the 1960s. Kempe et al. Studied the problem of selecting the best set of seeds that maximize this influence spread. And along the way, they show that influence can be estimated using polynomially many samples for the particular models that they had in mind that they studied. So what model are we going to focus on today? We're going to focus on the independent cascade model. So briefly put, the input is a weighted edge-directed graph where for each edge there's an assigned probability. At the beginning, there's a set of seed nodes S0, and at each synchronous step, each newly infected node tries to infect all of its neighbors with probability dictated by the edge weight, and they're going to succeed with this probability, and this process is going to unfold in synchronous steps. So, and what is the objective function that we'd like to estimate? The spread function, well, it's the expectation over the number of nodes infected at the end of the process, right? Given the set of seed nodes S0. So what is the sort of vanilla way we can, for estimating this expectation? Well, we sample polynomially many sample instances of the process, we take the mean, and that serves as a good enough estimate of the expectation. Well, what is the problem? What are the issues raised by this method? Well, first of all, how much local information do we need to know? How many of these neighborhoods do we need to know for doing this process? And two, how scalable is this? How many samples do we need to take in order to calculate this estimate? And how can you do this in a parallel manner? All right. So first set of results is as follows. Well, throughout the paper, we rely on a particular model called the link server model, which assumes that we have some server somewhere where whenever we query a node, the server gives us back the neighborhood of that node, along with the respective edge probabilities. Right? And the first question that we ask ourselves is the information need of computing the estimate, which is basically the query complexity. So our first result basically says that in order to get an estimate that is about a third multiplicative error away from the true expectation, the value of the influence function, then we need about square root of n queries in order to do this with sufficiently high probability. The implication is that we need to look at a large portion of the graph. So given that we need to do many, many queries in order to compute this estimate, we ask ourselves, how can we parallelize this in order to scale for large networks? So in order to do that, we turn to the Mrc model, which sort of gives a principal way of analyzing the MapReduce algorithms. So briefly put, it goes as follows. So it goes in synchronous rounds. The input is throughout the algorithm we deal with key value tuples. We start with n key value tuples, and on every round we do a map step where we just stream over the tuples, and we do sort of these local transformation. And then in the following reduce step, we do polytime computation on aggregates of tuples. And according to the Mrc model constraint, given that the number of tuples is n, the constraints are as follows. Well, first of all, we have to have a sublinear number of machines. Each machine should have sublinear space, and we can have at most polylog many rounds. All right, so it's a pretty stringent framework. All right, so what's our approach? We're gonna so overall, we'd like to sort of emulate this sampling process using a MapReduce framework. So what are the main challenges? Well, first challenge is that a single sample may require a lot of space, right? So for example, in this case, just a single sample gives a linear number of tuples, right? Because a linear fraction of the nodes become infected as a result of infecting this single middle node. Second challenge is that many samples may be required. And why is that? For example, in this case, if we have a clique with edge weights of 1 and there's a single seed node, outside seed node connected by very low probability, just detecting the single instance in which this single outside node manages to infect the entire clique takes a lot of samples to detect. Why? Because it happens with very low probability, but it has a pretty considerable impact on the expectation, right? So we need a lot of samples. So again, we're going to do this in synchronous rounds, and the question is, how do we parallelize this? So what is the MRC MapReduce algorithm for influence maximization? So our goal again is to design an MapReduce algorithm that approximates the influence function f with high confidence. All right. So what is our main theorem for this part? So informally put, we give a 1 plus 8 epsilon, where epsilon can be as small as we want, approximation with polylog rounds, okay, with high probability. So our approach is as follows. So we take a sort of modular approach. So we have 3 subroutines where one uses the previous one as a black box procedure. So first of all, the first layer, we have a sample oracle where given L and T, in Peril, we sample L samples and we cap each of them at T. Second layer, and I'll go over this briefly. Second layer, we approximate sort of for a given guess tau of the influence value, we sort of figure out whether or not this guess is good enough by looking at sort of the 1 minus CDF function of the influence value, and we sort of figure out whether or not the guess, if the influence value is higher than the tau value, the guess, then we output yes, and we're good to go. This is the right guess. The last layer, which sits on top, just iterates over different guesses, and sort of it runs the previous layer and asks, is this guess is good enough? If this guess is good enough, return true, and we'll return the current guess, and we'll stop whenever we get a good guess. All right, so this is the high-level picture that we need to keep in mind. So let's, in a bit more detail, let's go over each of these layers. All right. So first layer again is bounded parallel sampling of the influence process. So what do I mean by that? So in parallel for L and T, we're gonna in parallel take L samples of the process, and we're gonna cap each of them at T. So whenever a sample reaches T nodes at most, if ever, we stop it. So how does this work? And this should be fairly familiar to HPC people in the crowd. We just do a boundary expansion, right? So we do sort of a probabilistic breadth-first search, and we expand one layer at a time. And if the diameter is polylogarithmic, then the number of these rounds is polylogarithmic. And so the map stage is just node-level infections. Each node tries to infect many, many times its neighbors. And in the reduce step, we just aggregate these results and we move on. And the challenge is how to address the cases in which the number of infected nodes blows up in a single step. All right? And I want to make it clear that we can plug in any other reachability algorithm with some required modifications, and that'll work just fine, and it'll impact the approximation ratio accordingly. Second part is the second layer is a verified guess for the true influence. So for a guess tau, we ask, is it close enough to the true influence function? So we sort of, at a high level, we sort of approximate sort of this area under the curve, this integral, which sort of corresponds to the expectation that we'd like to do it. But we don't quite do it. We approximate it using Riemann sums, logarithmically many rectangles, where the height of these rectangles is given by the previous procedure, sampling procedure, right? So that's how we use the previous step. And a useful principle that goes throughout our paper is that higher influence translates to fewer samples and vice versa, and that goes a long way to reducing the amount of space required throughout our algorithm. Top layer, which is our main algorithm, which we call infest, just iterates through guesses and tries to and asks the previous layer whether or not the current guess is right or not. If it returns yes, output the current guess, and we're good. And so this gives us a 1 plus 8 epsilon approximation to the true influence value, and it takes polylog many rounds, assuming that the diameter is polylogarithmic in n, and it's a linear number of tuples per machine, so it adheres to all of the MRC requirements. All right, so this is how it works, so it just iterates through tau values. All right, so just a few words on empirical results. So we did a bunch of empirical tests. We ran a bunch of tests, and I'm going to present two sets of tests in this in this talk. So one pertains to the running time of our algorithm. So we want to test the speed up and the running time. And where the benchmark is the naive polylog many samples Monte Carlo algorithm. So as you can see, our algorithm does quite well and several orders of magnitude better than the naive algorithm, and again, better than the algorithm which takes fewer samples. So not as many samples as the theoretically required number of samples, but still it performs much worse than our algorithm. And also our algorithm does better and better as the number. So on the x-axis we have the number of seed nodes. As we have more and more nodes, our algorithm performs better and better because we stop at earlier tau values, early guesses, whereas the naive algorithms do worse and worse because the infection goes larger and larger. This is monotone. Second set of results pertain to the approximation ratio of our algorithm. So we tested our algorithm on several networks and with several epsilon values, which measure the precision. And as you can see, it fluctuates quite a bit, but I just want to make it clear that all of them range between the allowed error range, and moreover, in many cases, they perform much better than what theory predicts. All right. So again, for a varying number of seed nodes, we measure the approximation ratio with respect to the theoretical algorithm, naive algorithm. Just to wrap up, so influence estimation in theory requires polynomial time computation, but in practice, this isn't feasible. So we'd like to take advantage of recent results in parallel computing, and we design MapReduce algorithms for doing so. Next steps, just 2 points, 2 directions. We'd like to look at other influence models. We may require different approaches. And second, influence maximization. How do we use these methods for maximizing the influence given a cardinality constraint on the allowed set of seeds? Thank you. Sure.
So how stable because there have been recent results reproved by Cascade et al. About the high sensitivity of all influence estimation to even small levels of noise in the input. So how sensitive are your approaches to noise in the input?
So the question is about sensitivity to noise. So what do you mean by noise? And noise in what? In the parameters of the graph, the function?
And parameters of the probability of transmission for different models.
Yeah, good question. So in terms of the approximation guarantees that we get in approximation ratios, we still get, we're pretty stable. So our approximation ratios remain well within the allowed theoretical range. Regardless of how we measure the edges, how we vary the edge probabilities.
You lose some modularity.
We may lose some modularity, but we don't need some modularity for what we do. You need some modularity for the influence maximization problem, but you don't need it in our case. So we didn't make any use of some modularity in our case at all. Yeah. Yep. Yeah, so we use 3 methods for generating these edge weights. So some of them have a lot of noise. Yes, so the question is, how do we generate these edge probabilities required by the model? So we use 3 methods. 2 of them admit a lot of noise in the edge probabilities, which sort of relates to what you just asked about a lot of variation. One of them is uniform from the interval 0, 1. Another one is a uniform selection from a fixed set of edge probabilities. I think it was 0.01, 0.1, and 0.001, something like that. All of these are sort of been tested. They've used these methods throughout all of the literature, and I think that's pretty much it. Oh, and also fixed probabilities as well.